Okay, so in this video what I'm going to show you how to do to solve this problem of a gate hanging here. So the gate is mounted with two hinges, A and B, and for additional stability here there's a cable that's coming off the end of the gate, goes up to a support here and holds everything nice and rigid. The gate is 4 meters wide, 2 meters high, there's an angle of 30 degrees right here, and as you might guess there's a tension in this rope here. So the first thing that the problem wants you to find is what is the tension in this cable right here, so why don't we set off doing that. Now we know that when we look at the gate as it's hanging like this, it's not moving, so it's a classic example of a statics problem here. And successful solutions to all statics problems here, you should recognize that the sum of the x forces is equal to 0, the sum of the y forces are equal to 0, and the sum of the torques are equal to 0. These three equations can always guide you through statics problems, so let's just apply one at a time until we finally arrive at a solution. So what we should do then is when we see force equation like this is of course go back to the original drawing and try to identify all the forces that are acting on the gate. So a couple that I can see right off is the weight of the gate, which is listed at 500 newtons here, and so the weight of a gate will act through its center, so I can draw a big downwards weight vector like this and label it W sub g, weight of the gate. The other obvious force that's touching the gate is this tension in the rope right here, and so if I draw a force vector coming right off this point of contact, pulling away from the gate there, I can label it T, and that's the tension in the rope and one of the things we want to find. There's two more forces acting on the gate, which are the forces that these hinges exert here. I find it easiest in the statics problems here to break them up into their components here. I'll call this one here B sub horizontal and this one right here B sub vertical. So two components of the hinge force right here. In general it's a vector, but these are just the horizontal and vertical components as I've labeled them there. The same thing will go for hinge A over here. There'll be A sub horizontal like this, and this one up here A sub vertical. Now sometimes you ask about, did I guess the directions of these forces right? And I won't know that until the problem's done, but if I solve, for example, for A sub h or B sub h and get a negative number, it just means I drew it in the wrong direction. A sub h, for example, if it was negative, would just point in the opposite direction. So I think that's all the forces on the gate, and with that in mind, why don't we just proceed and fill in this equation here. The sum of the x forces is equal to 0. So if you look at all horizontal forces on this gate here, I see two of them here. I see the two horizontal hinge forces here, so I can write A sub h plus B sub h. And the other horizontal force I see, which isn't obviously drawn on the figure here, is the horizontal component of the tension right here. It'll definitely point this way like this. I'll label it something like T sub x. And of course the y component, which we'll need in a moment, will point up like that, T sub y. And you can see that this is a 30-degree angle. The T sub x will involve the cosine, the T sub y will involve the sine, and we can relate all those components that way. So continuing on with some of the x forces equal to 0 here, I can see that there is a x component of the tension pointing towards the right here, pointing towards the left. So I'll label that minus t times the cosine of 30 degrees. There's my x component of tension. And if I look back at the problem, I think those are all the x forces acting on the gate. That completes the sum, and all those are equal to 0 because I'm in this case of doing statics now. The next equation tells me the sum of the y forces instead equal to 0. So if I again look at the gate, what force do I see along the y-axis? Well, I see a vertical hinge force due to hinge A, a vertical hinge force due to hinge B, and a vertical component of tension, and one more will be the downwards component of weight right there. So I'll go ahead and fill those into this second sum right here, which will be something like A sub vertical here plus B sub vertical plus t times the sine of 30 minus the weight downwards, all that's equal to 0. These are all the y-axis forces I see acting on the gate, so I sum those instead equal to 0. The last one I can use now is the torque equation. And of course, using the torque equation, our good old working equation for this is that torque is equal to r times f times the sine of phi, where this is the length of the moment arm, this is the force in question, and this is the angle between the moment arm and the force. So what I'll do then is I'll just try to identify all torques on the gate, sum them and set them equal to 0. As we discussed in class a few times, there's always a good and bad way to choose a pivot for a rotation problem here. I would choose a pivot right down here at this lower hinge right there, and one of the reasons why I'm doing that is because both of these B vertical and horizontal forces, because they're going to be at the axis of rotation, they have 0 moment arm, they won't contribute to the torque, and it'll make my work a bit easier. So I would think of this big dot right here as my axis of rotation. So if I just go ahead and identify some torques, well, I can look at these two up here. Both of these forces here, AV and AH, have a moment arm that's 2 meters from the axis of rotation, but I can knock a couple of them out already because A sub v here, if you look at it, is oriented parallel to the moment arm, and that's 0 degrees. And in my working torque equation, the sine of 0 is 0, so there'll be no torque due to A sub v. So it is a force acting on the gate. It's real. The force is non-zero, but it doesn't present any torque on the gate because of its orientation. I can do the same thing for A sub h over here. Moment arm is 2 meters from the axis of rotation. It points to the right, and there's a 90-degree angle in there. So I can go ahead and write that down to be something like, here's the moment arm, 2 meters. The magnitude of the force is A sub h, and the sine of 90 is just 1. Here's the 90-degree angle in here, and so I'll just write a 1 implied here. I just won't write anything. Now if I keep going through the problem here, I don't have to worry about BV and BH because they are at the axis of rotation. The moment arm is 0. I've taken care of this hinge here. The last two forces which can possibly torque the gate, of course, are its weight and this tension right here. You can imagine the weight sort of torquing the system down clockwise in the positive direction, and this tension here sort of pulling the gate up counterclockwise in the negative direction. So this is the sign convention I'll use for the torques. Okay. I think that this first torque here due to A sub h is a positive number, because I would imagine if A sub h had its way, it would cause the gate to rotate in the clockwise direction. So that's why there's a positive sign right there. I can proceed with the tension now. It's a bit tricky now. You have to identify the moment arm, but you can be okay if you remember the definition of moment arm. It's the distance between the axis of rotation and the point of application of the force. So I can draw a nice long line that goes over here like this, and this line I just drew here is the moment arm for the tension right here. So the moment arm, of course, I can find from the Pythagorean theorem here, square root of 4 squared plus 2 squared, and for that I get a number like 4.5. I'll put a minus sign right there because if this tension had its way, it would cause the gate to rotate in the counterclockwise direction. There's a moment arm of 4.5. The force is, of course, the tension itself. And if this is the moment arm and this is the force here, here's the angle between the two. It's clearly not going to be 30 degrees. That's only looks like, you know, something like half of the angle, but there's another section right here. You have to do a bit of geometry in these problems at times to figure those out. But I have a big triangle down here. If this side is 4 and this is 2 here, I can use an arctangent to determine that this angle here will be 26.5 degrees. And likewise, if this is 26.5 degrees, this will be 26.5 degrees up here. Now I see the full angle between the moment arm of the tension and the tension itself is 56.5 degrees. So I can fill in a sign of 56.5 degrees there as the angle between the tension and its moment arm. There's one more torque on the gate. It's the weight acting through the center. It's found similar to the tension. Only the moment arm is about half now because it only goes halfway through the gate. And the weight acts at the midpoint of the gate. So this hypotenuse right here is now going to be about 2.2 meters from the axis rotation to the point of application of the weight. That's the moment arm. It's going to be a positive direction of torque here because it's going to be a clockwise rotation. So 2.2 times the weight of the gate times the sine of, well, what angle now? This is 26.5 degrees right here, and this little triangle right here is certainly a right one, so there's a 90-degree angle, 26.5 degrees. So if I put some of that together here, this angle right here will be 63.5 degrees. That'll be the angle between the moment arm to the weight and the weight itself, so I'll put a sine of 63.5 degrees in there. So I have this rather long torque equation. There's the horizontal hinge force, there's the tension, there's the weight. Those are the only forces acting on the gate. They're the only possible ones that can generate a torque, so all they'll be equal to 0. There's my torque equation. Now if you read this particular problem carefully here, they say they want you to consider the case where the horizontal force due to this top hinge is 0, so AH is going to be 0, and you can see right off that if you were able to set this term equal to 0 here, this torque equation becomes a minus 4.5 times T times the sine of 56.5 plus 2.2. Now the weight of the gate was listed at 500 newtons times the sine of 63.5 degrees. All that'll be equal to 0. Looks like a big equation I can just solve for the tension. Indeed, I'll just do that right here, and I get something like 262 newtons. Now if you look in the back of your book or the solutions manual online, they have something like 268 newtons, but I found that's just round off error between the Pythagorean theorem that I did here and here. So if you replace these with the exact square root expression, you'll get your 268 newtons. So here's your first answer right here, the tension in the rope. If you want to proceed on now, the next question asks for this horizontal hinge force due to the lower hinge right here. Where would I get that? Well, you can look at one of the equations you formed, in particular the x statics equation up here. Again, A sub h is 0, just leaving an expression like this that says now the horizontal hinge force will just be T times the cosine of 30 degrees. You found the tension there to be 262. You can calculate the horizontal hinge force then to come out to be something like 262 times the cosine of 30 degrees. Okay? And lastly, the very last portion of the question says, can you find the sum of the vertical forces that the hinges impart on the gate? So the total upwards push of the two hinges, I think you can, because you have this expression right here.